All right. So that should be the recording starting. A few people might still filter in as we're only three past the hour. But today we have Szabolcs Horvát. Is
That's
that close? Good, great. Giving a talk on igraph and how it has supported multiple 4GL front ends for quite a while. And we at Bioconductor are potentially interested in including other non-R language-based tools in Bioconductor. So I thought that this would be a good topic for us to hear from. Um, that is my very basic intro. And I can hand the floor over to you. I believe you should be able to share your screen and get started. Is that right?
Let me just try that first. Okay.
Okay, great.
I hope this works.
Yep, I can see it. Anybody who can't will hopefully let us know. Um,
So
but yeah,
thank you so much, Nick, for the invitation. And I understand you'd like to hear more about the technical aspect and development challenges, especially as they relate to having interfaces to multiple high-level languages. Um, I do have some slides here, and I will go through just a basic intro to iGraph before talking about these topics, but I think it will be easiest if we try to make this more of a discussion. So, a message to the audience, please don't wait with questions until I'm done. Just interrupt me, just start speaking, and hopefully it will be a more useful discussion and a more lively discussion that way. So let's not leave the questions to the end. Okay. So, just a few words about me. I'm part of the iGraph development team. I'm not a professional software developer. I'm actually a network scientist, a complex systems physicist. I'm an assistant professor at the Reykjavik University in Iceland. So keep that in mind when you hear my perspective. I'm going to talk about what iGraph is, how we develop it, but I'm also going to give some personal opinions. So just keep that in mind as well. Some of it is that, and I'll try to make it clear when it's that. And I think that will be a good fit for uh, more of a discussion-oriented event. So as many of you might know, iGraph is a network analysis package. It was built for analyzing connectivity data, all sorts of networks. Um, Mostly used by network scientists, people analyzing social networks, various biological networks such as food webs, but also other things. This might be familiar in the middle to many people working with single cell transcriptomics. And it also, of course, has graph theory, more mathematically oriented functionality. We had a big release 1.0 quite recently, last autumn, but the project is actually 20 years old or even more than 20 years old. I've been personally involved only for 10 years. It was originally designed by Gábor Csárdi and Tamás Nepus, two Hungarian graduate students at that time, and then it grew from there. Originally, it was an R package, but very soon after that, it also got a Python interface. However, in the design of the code base, it shows very much that it had an R focus and an R inspiration, even inspiration from how R itself is designed. So some of our challenges were actually to get rid of some of that to make it easier to integrate it into other languages. I maintain mostly the interface to Mathematica, Wolfram language, and I started doing that about 10 years ago, so 10 years after iGraph was born. But these days, I mostly really just do the core algorithm development and work on the C code base. All right. Um, who uses iGraph? So network scientists, some of them quantitative people, physicists, data scientists, some of them more empirically oriented researchers, biology, sociology, also a few people in math, in graph theory, especially the mathematical interface. And it's also relevant for, well, I'm argues of software engineering. Basically, I'll talk about this later. Some of the user base, we see it as developers who write packages themselves, who depend on our package, on iGraph. So this is more of a personal perspective, but I'm hoping for an interesting discussion around this because the considerations to support two types of users, researchers, graduate students, academics, data scientists who sit at their computer and analyze network datasets versus package developers who need a stable API and depend on iGraph in their package. Okay, we do have a lot of dependence. This is not super interesting and actually somewhat outdated data with this graph. We have a lot of citations from Google Scholar, some hundreds of Python and R dependence. I don't have good statistics for Mathematica dependence. So let me talk a little bit about how iGraph is designed as a code base, as a software. It's written in C, not C++, but well, a little bit of C++, but it's written mostly in C. It's a C library with a C interface, but it's designed explicitly to be embedded in high-level languages such as Python, R, and Mathematica, which are the official interfaces, but it also has unofficial interfaces that people created to other languages, MATLAB, Julia. There were some attempts at Rust. Rust is not a high-level language. There was in the past a Haskell interface. There was in the past a Ruby language interface, and so on. On the topic of talking about development, I'm not sure I would really recommend C as a language for people anymore, but it's part of the challenges we deal with, that it's a 20-year-old code base. And that's how it was done originally when it looked like a good idea, and we're managing that. However, having a C interface, not a C implementation, did turn out to be quite useful because it makes it much easier to integrate it with other languages. Okay. So the C library also consists of two parts. There's a core API for a core graph data structure, which we try to keep as small as possible and the interface as stable as possible, the internal interface. And then around that, there is an algorithms library. Now, technically, these are in the same library, that in organization, we try to separate them with the hope that it would be possible to swap out the graph representation in the future if that becomes necessary. And in fact, that is one of the plans for the future. Another comment on this, and of course, it sounds like a nice design. It is a nice design to think about it like this, but when the API is designed for the core data structure and the core functionality, that really does constrain what one may or may not change. And there's many choices specifically for networks and graphs that must be made there. So in reality, the swap is not that straightforward. But okay, we can talk about this more if there's questions. So most people don't use it in C, most people use it in R. Second most popular is Python, and third is Mathematica. Okay. We try to be a very good software citizen for high-level languages. So the library is designed specifically for integration into high-level languages and has a bunch of features which are not universal. And among other similar libraries implemented in some low language like C, C++, or Rust. So one of them that I am very proud of is that it's interruptible. Almost every single function in the library is interruptible. What this means is that if you use R and start a calculation and I realize, well, this is going to take for half an hour, I better stop it, then that is going to work. Our users are used to this. Sometimes they expect it to the extent that they don't even think about the difficulties of making it work. But if the functionality is implemented in C, it's not entirely trivial. This is designed in and it works very, very well. As in, I wouldn't be able to give you a percentage, but almost all of iGraph is interruptible. It's not just interruptibility, it's actually a little bit more. I will also say at this point, I forgot to say at the beginning, I'm not really an R person. That's not my main language. I do use it occasionally. So you might have comments about what's specific to that, and please again interrupt me and do comment. But one thing I'm aware about R is that at least the Windows graphical interface seems to use some sort of cooperative multitasking, meaning that if you run a long computation that is not interruptible, then it will hang the GUI. So this also serves as letting the GUI update by handing back control. It doesn't just let the user interrupt, it lets other parts of the software update, which means that the library is a good fit also for integrating, say, into graphical interfaces, which are more simply designed. This is also supporting some functionality in Mathematica, all beyond just the basic interruptibility.
Actually, so I have a question since you did
Yeah,
invite us to interrupt you. So so one of so I guess kind of two questions. If you mentioned like you're not the like R is not your primary language, I was wondering, is there someone else in the core team who tends to like field R related issues?
yes,
Um,
absolutely, absolutely. So
and who
as
that
it's
is?
common with open source projects, it's volunteer based, right? And I'm actually going to check the participant list really quickly to see if any of our R people showed up.
I'm
Oh,
here.
yes, Kirill is here. Kirill, maybe you can introduce yourself. So Kirill Müller is the current R maintainer, R interface maintainer. He's the real R person. We do have an owner of each interface.
Okay, awesome. So also my second question was, since you're talking about GUIs and I guess some issues specific to Windows, this is kind of like a big pain point, right? Because if you want to work with very large graphs and like the hundreds of thousands of nodes, like any CPU-based kind of software tends not to handle that like very well, especially rendering and kind of sort of force calculations to visualize well. And I'm not very familiar with this, but I know there's like a project that's maybe 2 or 3 years old. That's Cosmograph that does use sort of this GPU native rendering. And I was kind of wondering, um, like what your thoughts and experiences are with sort of very large, like visual on the visualizing side of things. Even I because that's something that you cater to even if you don't explicitly do yourself. And I was sort of wondering if you could comment a little bit about that.
So if I got it, you're asking about visualization, you're asking about GPUs. That's a very good
Yeah.
point, actually. iGraph is not really a visualization library. It won't draw, but it does have core visualization functionality as in it calculates where to put the nodes of the network, right? To
Okay.
make a nice drawing. That is really the more graph theory oriented on, part of this. And it is computationally expensive. So it makes sense to parallelize, it makes sense to put it on a GPU, and having it both interruptible and parallelizable and GPU friendly, that does not seem to be very easy. I'm not going to
Right.
say it's not possible. I don't have that depth of knowledge, but I have the impression that it must be a rather difficult thing to do. So this is one of those trade-offs. Of course, we do have the goal to figure this out, and I've spoken to other um, to maintainers of other network packages, which are also written in a low-level language like C++ or C, and have high-level interfaces. So you want it to be interruptible, but nowadays you want it to be parallelizable. And there is nothing that can do this. There is one library which has some claim of doing this, but it turns out that they're either interruptible or parallelized, not both at the same time. So that is a challenge. And if anybody has experience with this, we're very interested in hearing that. With GPUs, it must be an even greater challenge. It's the same thing. So there's a trade-off, interruptible versus doing that,
I
seemingly.
see.
I'm sure there is a
And
technical solution, but it doesn't seem to be that easy to figure it out.
right.
Okay.
So if I
But
could
you know,
actually ask about this too. I mean, and from a user perspective, I guess it wouldn't be that hard to have like if you had a function that diverted to a GPU implementation, like asking or making it clear that that becomes no longer interruptible, like that is a thing that's possible. But on the portability side, like iGraph works everywhere. That's one of the points that you've made, and it seems like that's borne out everywhere. But like GPU implementations aren't. Like, is that something that you've talked about? Like, would you fold CUDA into iGraph, even though so many of your users are just not going to have any like CUDA installed, right?
Okay, so this is more of a personal opinion. Kirill may disagree. But I don't think that is really in the short term feasible to go at the GPU route for us. I think the more immediate goal would be just CPU parallelization. That would be a major achievement. As I said, it's an old code base. It needs some changes to make this happen, especially if you want to maintain the nice features that I'm going to list here. Soon we'll have all the 5 up on the screen. But I will mention 2 things I'm aware of. So there is another library, probably the most popular one in Python, definitely NetworkX, that you probably heard about for networks. And they have an interesting design that they introduced with version 3 where they call it a dispatch mechanism. Basically, it's possible that you're using NetworkX and they can load another library which is allowed to override some of the implementations. The interface stays, but the implementation is overridden. And I know that people have done this with implementations that use the GPU. In particular, I know that there's a project called Graph BLAS, maybe that would be a long time to go into, which is, if you know BLAS for linear algebra, it's the same spirit, and it provides high-level building blocks for graph algorithms. And the building blocks generalize to GPU, CPU, various kinds of hardware, parallelize, and the user who programs, the programmer doesn't have to think about this. So these are two things I would point you towards which try to solve this. One is the dispatch mechanism. The other is high-level building blocks, Graph BLAS, BLAS. Okay, so interruptibility is one nice feature. Another one, maybe I should not do this a second, but I should talk about, well, we have good hooks for error and warning reporting. So this is built into the C library. If there's an error, then it is easy to convert it to the host language's error concept. In R, it can be an error. In Python, it can be an exception. In Mathematica, it can be what is called a message, and so on. So there's hooks. You can provide your own function that gets called when an error is raised, and that can do what is necessary to report that error properly for your host language. This is actually closely related to the interruptibility, because when an error occurs, then you also need to clean up any allocated resources, memory or other resources. This same happens with interruption. And you need to do this without interfering with the host language's error reporting mechanism. For R, it was a little bit of a challenge because R loves to do long jumps. So when the standard mechanism, if I understand it right, and again, Kirill may correct me here, is that if you just use the standard error mechanism, you call the error function, then the flow of control leaves your code base and you don't get to do your cleanup easily. But this can be made to work. So this is number 2. Number 3, it's designed to integrate with the host language's random number generator. So many of our functions are stochastic. If you want to repeat the same output for the same input, you want to set a seed, you can just use the host language's seed function, and that is enough. It also propagates the host language's random state. Now, some people will say this is debatable whether this is really necessary. Some people argued with me that maybe you can just use the host language's random number generator to get a seed and then use that seed on your own RNG. But if you want to be mathematically diligent, then there's trade-offs between RNG quality and speed. So there are some fast ones which don't pass all statistical tests. So now you really have the choice to choose something that you trust if that is a priority in your project that is high quality. And this works again for all the languages. R is a little bit weird in how it deals with this because it loves to use floating point numbers instead of integers. And in the C API for R, the main way to get random numbers gives you floating point numbers, not integers, when precision becomes an issue. So if anybody's interested in this, I can tell you
So
stories about how we dealt with it.
I kind of have one question about RNGs. So I'd taken a evolutionary biology class a long time ago, and as far as I know, this professor is the only one to do this, but he actually would create all his like RNG like random samples up front and then use them. Like I'm just trying to think like from a reproducibility point of view, like do you see those patterns? I know like trying to ask using the core development and think about how people apply it, or like maybe it's kind of out of your view, but I was just kind of curious if you encountered that, or maybe Krill if you
I'm
have
not sure.
encountered.
I'm not sure. I'm understanding the point of the question.
So
Maybe I need some clarification. You can, of course,
yeah,
it doesn't matter if you have your numbers and use them. I mean, in older times, if some people seen this, when people needed high quality random numbers, there's books published with numbers. You have a list of numbers that you can use for your Monte Carlo calculation. So that doesn't really matter. But I guess that's not what you mean. You mean something that's related to the implementation
well, yeah.
challenges,
So
right?
you can think of like let's say you're trying to compare different models with different sets of parameters, and you want a certain parameter to have like the same random samples throughout. But if
Yes.
you add another parameter, maybe, and that pulls a sample, right? You can see how that would change like some of your comparisons. I'm just kind of curious um, if there's like particular if that's something that you guys pay attention to, or you have some suggestions of how to use or
I'm still not entirely sure that I get the question, so please correct me, but I'll try. Maybe so a major example where we get a lot of feedback from biologists for some reason is community detection. So it seems to be the case that many of the single cell sequencing data is being clustered with network-based methods that are mostly implemented in iGraph. And then sometimes people who are not so much on the quantitative side but do this get surprised that they run their clustering method once, they run it again, and they get two different results. Which one is the right one? Which is the right result? We are very aware of this, and actually we try to support users not just by providing software, but also by providing education in the documentation. We are going to publish soon a tutorial. The draft is actually online already, which shows partly how to deal with this exactly, and partly how this is a good thing in the sense that if you run your clustering many times and get very, very different results, then maybe there is no good cluster structure in your data. If you get roughly comparable results, then maybe there is. So this can even be used to evaluate that. There's sometimes requests to us that, say that I used this method, sorry, and I used this seed and I got a result. And now you change the library and the result is different from the same seed. And that's a big deal. Well, actually, my answer to this is that if it changes, then maybe that should be taken into account in the analysis. It's not really realistic to guarantee the same output for the same seed across versions. It's just technically hard and it prevents bug fixes, right? So we don't do that, but we do pay attention to guarantee the same result in a statistical sense. Statistics shouldn't change if you run it many times.
right. Okay, thank you.
Does this get closer to what
Yes,
you're
yeah,
asking?
yeah.
Okay, so host languages RNG, we hook into that. Of course, a big deal with network data is that you want to attach other data to vertices and edges, and that's done in a way that there's an interface that allows you to use native objects of the host language. So Python objects or R objects, R expressions as edge attributes and vertex attributes. And there's also, although this has been ignored a little bit, so not every function has this, there's even a progress reporting functionality. So there's an API in the core library which allows functions to report how much they're done. So if you were to integrate it into a GUI interface, you can have a nice progress bar. This does work in R. I'm not sure if it still works, but it worked in the past. It is a maintenance burden, to be honest. So it may not be that well supported anymore. But the idea is there, it's feasible, and it might come back in the future. So all of these focus on how do you integrate well into the host language. we do try to take two types of usages, so to keep two types of usages in mind. So people using high-level languages are sometimes end users, data scientists, researchers. They love to use notebooks for exploration. We keep that usage in mind. We try to support it in various ways. It is possible, for example, in Python to expose the progress bar and in Mathematica as well in a notebook and watch how far along your calculation is for certain functions. Some other people like to write scripts, or some other use cases prefer write scripts that run once, maybe even on a computer cluster. Okay. I'm not sure, in the interest of time, if I should skip this part. This part is about, how igraph is different from other network libraries. One thing is that we really do try to be mathematically principled, diligent, and quite general in our implementations. So various functions fit together well. There's a bunch of choices to be made. Here's a question. If you have only one node, is that still a graph or a network? If you have 0 nodes, is that still a graph or a network? Is that actually useful and relevant? If you have 0 nodes, is that a connected graph or not a connected graph? Is that a tree or not a tree if trees are supposed to be connected? So this is consistent. This is an example of generality. Our betweenness calculation doesn't just do standard betweenness. It has a bunch of functionality integrated into it. You can have a cutoff for shortest path lengths for people who know how betweenness works. It can have a restricted shortest path source and target vertex set and so on. It can weights and so on. If there are weights, we do comparisons, and I realized that just as I was putting this together is an old slide, so there's a bit of a, so these are not accurate, but they make the point. So if there are weights in your graph and you're calculating, for example, shortest paths, then if you use floating point numbers for your weights, these are rational numbers, 2/3, 1/3, you add them up, you get a multiple of 1/3, right? But what you end up getting may not be the same floating point number. So if you don't perform comparisons with tolerances, then you may not realize that two paths really have the same length, which will distort betweenness results. So we do pay attention to these kinds of things. We spend quite a lot of time thinking about it, and these things are done well. Okay. Some recent news of what we've done. So one of the big things I'll talk a little bit about more was the 0.10 release. And now we have a 1.0 release. So all the R library was updated to use the 0.10 release, which partly served to really get rid of the R-isms in the implementation and make it more general, made it more work. And an R library which is based on the 1.0 release is coming soon. Kirill, do we know when?
So first, we're going to break all the downstream code by just updating the R interface. This breaking just means that we standardize argument names, and so we introduce the ellipses to put optional arguments past the ellipses, so they have to be properly named and spelled out. This allows you to easier extend and
I will
adapt the
interrupt you a
feature.
little bit. Maybe it is best after I show stimulus, right?
Well, the question is going to be Q4, but let's continue.
Okay. I'm sorry. And can you do interrupt me also anytime that you want to add something? Okay, so
sure.
We have a 1.0 release, which has a big interface reorganization, the C library to make it more logical and easier to maintain. We have now, so we are trying to be very portable. We run on many platforms, not just are able to host the library in many languages, but run on many platforms, including in the browser. As I said, the library is designed to be embeddable into high-level languages, and there are third-party projects which do this. There is now a MATLAB igraph done by David Connell. there is a project, as you can see, still active. 2 weeks ago, there was a commit today, 2 weeks ago, to make igraph usable from Julia and so on. If there are any other network people here who work with network science or network software and you don't know about NASCAL yet, do look that up. This is a few years old news, but we did set up an organization for developers of network software to collaborate with. It's called NASCAL. If you do develop network software, definitely look it up and contact us. And one of the big news items is that if we manage to get resources, then we can finish this. A new Python interface is in development, and why this is going to be a big benefit, I'll tell you soon. Okay. I'm going to skip some things here to move more to the discussion part and not to go over time. So I told you about how igraph is 20 years old. It got a really big kind of a push when we got a grant around 2021 for development, which resulted into 0.9 and 0.10 releases. So why is this interesting for this talk? It's because, as I said, it was very much inspired by R at the beginning. There were several R-isms in there. One of them, maybe some of you do encounter this difficulty, is that R really loves floating point numbers. Even if you have integers there, like indices, sometimes internally they're floating point numbers. And back in 2005, 2006, igraph adopted the same design and ended up using floating point numbers in places where they don't really belong. So we did a fairly laborious and large-scale reorganization to get rid of this and have proper types for proper things. Things that represent real numbers for a real-world network, such as how much flow in a blood vessel, maybe. That's a floating point number. Things that are indices, vertex indices, edge indices, indexing into vectors now is properly integers which are switchable. You can choose to compile for a 64-bit target, for a 32-bit target. You can compile with 32-bit integers, even on a 64-bit machine, if you need to prioritize memory use instead of something else. And this also allowed for a while to move the R interface together with changes in the C core, because at that time, and I believe still today, R internally mostly uses floating point numbers. It does have integers, but only ints, so only 32-bit. It doesn't really have native 64-bit integers in its C API. So this was one of the big achievements. 0.9 was some interface reorganization, some necessary updates catching up after a bit of a hiatus. And 0.10 was really decoupling it from R so it can fit more other languages and cleaning up the integer types. And this is an old chart that I borrowed from an old presentation because GitHub will not generate this activity chart for me anymore. It says that the project is too big for it, so I couldn't update it. But last autumn, I think in September, October, we had the 1.0 release, which built on 0.10, mostly by rationalizing the API for specific functions. There is no major breakage, but a lot of functions had extra arguments, had a more sane, easier to deal with interface, and so on. So a lot of little things. Okay. Development challenges. Some lessons and some personal opinion as well. So warning about that. For big projects, so licensing. igraph is copyleft licensed, GPL licensed. This is mostly for historical reasons. In 2006, that was standard for open source scientific software. So if you'd ask a less experienced person, a researcher, what is a proper open source license, they would even equate GPL with open source, which is of course not the case. Today, this is not fashionable anymore for various reasons. We are not that set on GPL, but we accumulated a lot of history which ties us to GPL. There were contributions by many people over the years. Some of them are difficult to reach. And we would need their permissions to move away from GPL. There are libraries which igraph depends on, which might be difficult to replace, which are GPL licensed, and so on. So really, the message here is that if you start a new project, then think about this very carefully. Think about not just what license you choose, but what flexibility to give yourself to make changes in the future as the world around your project changes. It is clear, at least to me, that permissive license like MIT or BSD would be much more beneficial now, but making that happen is no longer easy. Anybody else dealing with a situation like this? Okay. Another consideration which I thought could lead to a discussion is what kind of users do we have? How do we explore the user base? And how would we serve our users best? So I talked about this. Some of our users, I see them as end users who sit at their computer and analyze data, usually academics, sometimes data scientists, and so on. Some other users are package developers. Since you all deal with R, you know about reverse dependency checks, which are basically required for getting your package on CRAN. That is a very good way to see if whatever you do is going to make the life of downstream developers difficult, but it doesn't really tell you what effect you might be having on your end users if you have end users like this. And I think most scientific packages do. So my message here is really just, I'm not sure if others discuss it in this term, but this is how I think about this issue. When we map how many people use our package, we can look at the number of dependencies. That doesn't tell us much about end users. If we look at reverse dependencies, does a change in igraph break our dependence? That affects package developers, but it might affect end users very differently. How do you even explore who your end users are? Maybe you have a forum, maybe you have a strong community, maybe you have a lot of discussion. That's a good channel for information. Maybe you develop a GUI program, not a package. In that case, you can collect statistics about end users. A lot of GUI programs do that. Packages, like R packages, Python packages can't really do that. So there's, I think, also a danger that by forgetting about end users, focusing too much on developers, we can really make the life of our core users more difficult than it should be. So this is just, food for thought. It also induces other trade-offs that's good to consider. If you look at package developers as your main users, then a big priority is API stability, right? You don't break anything. If you look at end users, then maybe what you want is to bring out functionality as fast as possible. There's a new method, you implemented a new method, you want to get it out to people so they can start using it. And you also want to get it out to people so they give you feedback about how they actually use it. It's especially important if the developers are not always the users themselves. Some of us at igraph are both developers and users. Some of us are not, but none of us are users of all the functionality, right? So we do need feedback from the end users. So what we do here is something that's very common for high-level languages like R. We have experimental functions where we don't commit to API stability, but it does become a bit of a battle sometimes when you do this for a C library because the expectations for C libraries are very different. If you publish a C library, it gets included in Linux distros, package systems like Homebrew or Nix or MacPorts or whatever. The maintainers from there will come and complain if the API changed. And even if you say, okay, well, that's an experimental function, it takes a bit of an arguing to change the mindset of how this is viewed by someone who is more used to strict API stability and strict versioning. So again, I don't know if anybody else here thinks about these issues this way or any experiences.
So Bioconductor has a fairly it encourages developers to be aware of this when they deprecate functions within the library or within their own packages. But I don't think that we have tools to enforce any of those warnings or any of those systems. So it's something that the core thinks about, but it is something that is difficult to get developers within the community to adhere to, I think would be the right way to say it.
So if anybody's interested in this topic, especially this lens to look at the issue too, like two kinds of users, developer versus end user. And I would really love to have a chat because it's also a project for me, a network science project. We try to find ways to explore these two aspects separately, not for iGraph specifically, but for various packages. And our packages tend to be the best data source because the ecosystem tends to be much better organized than say Python, much, much better organized. And we're trying to scrape data from GitHub with a graduate student that I'm working with, see if various repos are just for an analysis script for a package, which one of the two, what other packages they import or depend on, what are the differences between them, and so on. So I would love to have discussions about this after this, if anybody else is interested. Okay, something else. How do we really deal with multiple high-level interfaces, which was the main question here? So if you look around at other software that has interfaces to many high-level languages, then a very, very common approach is what I like to call just generate bindings. So maybe you have a library which is written in C, and then maybe you have an automated system that translates that C interface to Python or R or whatever, and then almost for free, you get bindings to many languages. The problem is that anything that's automatically generated like this with tools like Swig, for example, must mirror the C function very closely. And R is not C, and Python is not C, and R is not Python either. So anything you get this way is going to feel terribly low level and cumbersome. In some cases, users might even end up being forced to manage memory explicitly in a language where they never ever do this, to allocate things, deallocate things, and so on. So that's a cheap-ish route to get exposure to many languages, but it's not what we do here. Another route is that you have handcrafted interfaces. And this is what iGraph used to have. There was a handwritten interface to R, there was a handwritten interface to Python, there was a handwritten interface to Mathematica. It's a huge amount of work to do this. It's just not feasible, especially for an open source project that runs on volunteers. It's just not feasible in the long term. But of course, the advantage is that you have the choice to create a very well integrated interface that feels as native as possible. Of course, it will never feel as native for Python as a library that is as a package that's written in Python itself, but you can get pretty close if you use a handcrafted interface. You can make decisions about every function, how to expose it, and so on. So what we try to do now is try to balance between these two. And we do have a custom interface generator, which we call Stimulus. It's actually a pun in Hungarian, because if you put together the Hungarian words for interface and generator, then you get a meaningful word which literally means stimulus, like a neural stimulus. Okay, so there is a handcrafted interface generator, which I'm going to show you in a second. And this one still does generate what you might call, what I called bindings, a somewhat low-level exposure of the C library. And then we build on top of these bindings something nicer. But ideally, we try to do it in such a way that sometimes you need minimal changes on top of that, or you even need zero changes on top of that. And one way we achieve this is that the interface generator is customized to igraph and to igraph's specific functions, specific requirements, specific data types. So if you use a generic interface generator like Swig, then you can tell it you have a function. The first argument is an integer. The second number is a floating point number. The third is a vector. Here we have more specific semantic types. The first number is not an integer, it's a vertex ID. It's specifically a vertex ID. And then the interface generator knows how to generate code to pass a vertex there, which might be not referred to by ID, first, second, or third, but might refer to by name, if vertices of this network have string names. That floating point number might be specifically a weight of an edge, or it might be the length of an edge. This very specific distinction is not, for example, fully implemented, but it's easy to do so. Again, the vector can be various different things. So there is this sort of semantic information, and I hope that when I switch over here, this is going to show. You should see a browser. So we have a large interface definition file, which is maintained together with the C library. And for every C function, these are C function names. Let me find a good example. These are graph generators, not the... Okay, so here is, for example, a function which is going to tell you what are the shortest paths between two vertices. And then there is a list of the different arguments and their semantic types. So the first one is a graph, and that's an input. And then it can output the vertices or the edges of the path. And it's marked as vertex indices and edge indices. It's also marked as an output parameter because this is C. So in C, you can't return more than one value as technically a return value. You have to return it by writing it into a pointer effectively. So it tells you that. It also says it's optional. So when you use this system to generate an interface to R, then you can request to get vertices or not. You can request to get edges or not, because maybe you don't need both. Then from vertex to vertex, so from one point to another point, we want to find shortest paths. Maybe there's weights for the edges, maybe not, but again, they're marked semantically. And there's some extra information as well in how some of these quantities that are passed to the function are interdependent. When it passes out some vertices, which under the hood may be just a list of integers, indices of vertices, then it says that those are related to the actual graph that was passed in. So the system can potentially generate code that cross-references those. And you will really see the output showing up as vertices. If they have names, you will really see the names, not just the numbers, and it will be tied to a graph. So this is the principle of how it works. This was originally done for R only, and one of our basically ongoing projects to make it work for all the other interfaces. What we have is an interface generator that does potentially work for all other interfaces, but it's only implemented fully for R at the moment. And even there, when this was originally designed, it wasn't done for all the functions. It was done for a majority of functions, but some still had a handcrafted interface. So one of the things we're working on is to move everything to the interface generator. And then we have, sorry, my Zoom is a little bit overlapping with my browser, but we have an alternative new Python interface, which we hope will be much less effort to maintain while also be cleaner, which will replace the handcrafted interface with a generated interface. It already has a good chunk of the functionality, but nothing is stable yet. And unfortunately, our constraints are resources and how many hours we can spend on it. But if this is complete, it should really, really ease the maintenance burden for all the interfaces. So this is how we really we try to achieve this good trade-off between raw bindings versus a well-integrated interface. What this gives, technically speaking, right now for R is still just bindings. I can go to the R repo here and show you. There, it generates an R file, it generates a C file. Here is one of the R files, and you'll see functions like this. All this code is generated. It is checked into it is committed to the Git repo, but it is generated and it can be updated. And it makes a function from the click number function, click number C function, something that's called click number imp for implementation. And this may look nice enough to use it directly from R, or may need a little bit of polish, in which case we can do a light wrapper around it to clean it up. Most of these, the good news is, tend to be good enough that they can be used as is. Sometimes they're not for various reasons. One reason could be, for example, shortest path functions. There's many different methods to find shortest paths in graphs, all with their unique trade-offs in speed, for various requirements, if you want all-to-all or one-to-all, whether we have negative weights and so on. It's nice in a high-level language to have a single function for shortest paths, which switches the method that it uses automatically or allows the users to switch the method. But at the same time, you might need to have separate functions in C for this. Sometimes you have that for historical reasons, and it's hard to change it because of API stability requirements, but sometimes we need to have it because C is not a flexible language. You don't have a variable number of arguments. You have a fixed number of arguments. One method might have 2 extra parameters, the other 3 or 0. So in C, they need to be separate functions. In R, you want them to have a single nice interface. So you generate bindings for all of them and then write a light wrapper around these bindings that unifies them into a single thing. How much work is this really? Well, Kirill could comment more on that, but I will show you that actually it's not that much from a certain perspective. So this interface generator is not a major project. It's a fairly simple thing written in Python. It's not that many lines of code. There's generators for each language. There's a unifying generator. And the files are not that many line of code. Okay, this is about 400. This is probably the biggest one. However, most of it doesn't live there, but let me find this. So an interface file exists not just for the core C library, it also exists for the high-level interfaces. There is, for example, this interface file. So I showed you the interface file for various functions. There is also an interface file for various semantic types, which doesn't really understand the semantic type, doesn't understand the meanings. That's a convention that we know as programmers. It just gives the types names and maybe a very basic mapping to what kind of C type it will be. But on the R side, then, for the various types, there's a little templates that just help the system generate the right C code and the right R code for transferring that type back and forth between the R layer and the C layer. So basically, it's still in parts of the interface definition files or something attached to that where you write this code. You don't need to modify the interface generator system itself extensively. Sometimes you do, but usually you don't have to modify that extensively to adapt it to a new aspect of a language. It does need a basic template for a new language, but once you have that, then adding new types is just adding string templates that can be filled out with various variables. It does look a little cryptic, and it does need a bit more documentation, but it works pretty well in practice.
Szabolcs,
So I'm going
if I
to
could
stop a
interrupt
little
you.
bit here. Oh,
Yeah, we're coming up on the hour. I have at least one quick question, and I hope that other people do
yes.
too, because I really like this stuff. So these interface generators, they it you basically need one for every different language that you are sending functions to, and they're all calling on the same sort of stack of definitions for types. Is that an accurate description of them?
So there is one Python package called Stimulus, which is able to read these interface definition files. That is a single thing, right?
Okay.
Then if you look at the source code of that, for generators, there is something that's specific to Python. There's something that's specific to R. Long time ago in the past, there was a Java experiment. It's no longer live, even a shell access experiment. So you have this, but these are not usually huge files. It has some R-specific stuff in it. Well, actually, it's a little bigger than I expected, 600 lines. But after that, you just put in little snippets in a YAML file. All the rest is just YAML files. So this is just a YAML file where you give little templates for how do you handle various transfer directions when it goes from R to C, into the C, out from the C, from C to R, or a parameter that goes in and then it gets updated. And this is literally C code. What you see here is C code, and this is the bulk of what you need to write. So there's one system, and then this is the file that you really need to customize for various languages. Maybe it's more familiar. Here's one for the R side of it. So all that you see here is R code. For example, in this system, there's also default values. In C, you have a lot of parameters for a visualization layout function. So you can tweak things, but you just want a nice default that works. In C, there is no such thing as a default value. You can emulate it in various ways, but it's not perfect, right? So the interface tells you that what should be the default, and sometimes that's even computed. So sometimes it's the 10% of the density or something
Okay.
like this. And
If
this
I
is all
could
provided here.
if I could pause you again for a second, does anybody we're at the hour, so I'll probably end the recording at some point
Yes, I'm
soon. But
sorry.
does
I
anybody else? No,
forgot
it's totally
about any of
fine.
that.
Does anybody else have any questions that they'd like to ask before we do that? Um, I guess it seems like not. I do have one that I would like to get recorded a little bit. So the best of my knowledge, iGraph doesn't rely on OpenMP. Is that true?
A
And
little bit.
it does a little
No,
bit.
it's not.
Okay.
I mean, look, there are some functions whose implementation relies on OpenMP, and that's where we give up interruptibility. That's a small minority right now, which is a good thing for interruptibility, bad thing for parallelization.
Yeah,
I
okay.
don't think it's going to be really feasible to do proper interruptibility specifically with OpenMP, which is a real shame because OpenMP is easy, relatively speaking, right?
Yeah. Okay. I think I'm gonna end the recording here. I have a few more questions after we do that, but people are free to stick around or go. I know that we're a little past the hour and I don't want to encroach on anybody's time, but uh thank you all for coming. Thank you, Sabosh, for the talk. I really enjoyed it. I hope everybody else did
Thank you for
too.
the invitation.
And yeah, thanks everybody.